All right, so my name's Chris Gregg. This is Data Structures. I feel like I haven't seen you in forever, although I saw a bunch of people at lab over the last couple of days. So if you didn't go to lab, that's fine. You have to do it on your own, though. So please get the lab done to the best of your ability. Let's say before Thursday, but if you need a couple extra days, I won't turn Provide off until like next week, like early next week, sometime like that. So if you need help on the lab, you can still go to office hours and get help. My only comment is please prioritize homework 2 over lab. OK, so if you haven't finished the lab, that's all right. But instead of like trying to do the lab, try to do homework 2 and get that done. OK, I woke up a little grumpy today. Because so I went to all the labs yesterday, and I talked to way too many people who said, oh, yeah, I'm going to start homework 2 tonight, blah, blah, blah. And I thought, that's great, but I really don't want to see an email from you Friday saying, oh, I can't find these bugs because I blah, blah, blah. It's because you haven't had the time to find the bugs, right? So I really don't want to see a lot of emails saying, hey, I need an extra couple days. You don't need a couple extra days because you should have started the assignment much earlier than yesterday or today. So if you still haven't started it, you better get on it. Because here's the thing about the first assignment was a bit deceptive, right? It was pretty easy. We gave you all the functions. We gave you all the comments and everything. That's pretty easy. The second assignment, even though it's the same functions in the sense that most of the same functions, linked lists are a whole different beast, right? And there's lots of pointers and lots of things that can trip you up, right? So you really need to be digging in a little bit. And maybe, honestly, maybe it'll take 20 minutes to do this assignment. That's awesome. If it does, great. But don't bet on it, just because it just takes longer to debug. OK? So anyway, that's my grumpiness for the day. All right? Let's see. Any questions before I get going? On homework 2 or lab? Yes, Sal. Yeah, we're still more or less on track. We might be one lecture behind, so the mid-year will just cover a little bit less stuff. That's all. I mean, I won't change the dates. Yeah, I don't plan on it. I like the idea of having it a couple weeks before spring break and then going like that. So I don't think I'll change that. Yeah. Anything else? Yeah.
Are the labs based on completion?
Oh, yeah, good question. This came up on Piazza in lab yesterday. OK, so labs are based mostly on completion, in the sense that if you do it and submit something, you'll get most of the points for it. Right? I think the labs are out of 4 points. And each lab is worth I don't know, total labs is 10% of your grade. So really, it's 1% of your grade. Right? So I'll take 1 point off if you can't figure out how to get it to work, right, from each lab. So in the end, it's not the biggest deal in the world if you don't get the labs to work. We would like you to. But again, prioritize homeworks over the labs. OK? We would like you to take a little time, because too many people last semester and previous semesters kind of did the lab and then submitted something and it didn't even work, and they never got around to figuring out what those issues were. And I want you to take a little bit more time to try to make it work. OK? So I am going to grade it just a little bit. All right? So not the end of the world, but just a little bit. OK? All right. And we don't necessarily expect you to be able to do the labs by the end of the lab period. If you can, great. If you can't, well, OK, so maybe you don't have time the rest of the week to get it done. I mean, again, don't stress too much about that. Just do the best you can on them. OK? Anything else? OK. So last time we met, a year or two ago, we started talking about linked lists and then asymptotic complexity. In the meantime, we've had homework 2, which is almost ready to be turned in, and lab, which was on linked lists. So today I'm going to kind of fly through some last-minute linked list stuff, because you've seen it enough times, I think, at this point. And then we'll also just kind of review the asymptotic complexity rules that we talked about before. Well, not really the rules, but the types of asymptotic complexity, because almost every class I'm going to ask you something about asymptotic complexity. So you got to start thinking about it continuously. So we'll go through that. I won't really talk about the lab because you did that. If you have any other questions on homework 2, we'll do that. After we get done with this stuff, which should take about a third of the class, then we'll transition right into the next topic, which is on this abstract data type called a stack. Now, I understand that those of you who took Comp 11 talked about the stack and maybe some things about stacks. But we'll go into details about it. It's actually a pretty simple idea, but also a very powerful one. So we will do that. OK? All right. Now, I promised you a long time ago that I would show you some obfuscated C. OK? This is a C program. You can kind of see some things in it, right? Like you can see a pound include. And then let's see, there should be an int main around here somewhere, although I can't find it right now, which is not necessarily a good thing. But obfuscated. And notice it says fluid, like it actually, whatever. You can compile this. Like literally, you can say GCC, blah, 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 and it compiles, right? Which is kind of neat. The guy who created this actually won the obfuscated C contest a few years ago. And somebody was nice enough to post going through this on YouTube. And I will show you that. And it actually has music with it, which is kind of nice. And I'll pause it a little bit just to show you what's going on. But let's see. OK. So this is the program itself. What's going on down here is it's just compiling it, right? And it's just compiling it. And after it compiles, that's all a whole bunch of compile flags and things. And then what's going to happen is you can kind of, unfortunately, YouTube is not helping me there. What's happening is he's taking the program, the source code, and running it into his program. In other words, this program takes as input his program, which is interesting in itself, right? Watch what happens when it starts running. Yeah, what? That's a good question. What's going on? He has built a fluid simulator out of ASCII characters in that little one-page piece of code. I read something from him that said here's another one. He's going to pipe this basically into the program itself. It's kind of neat, right? He basically made it generic, and it does this fluid simulation. He says that his wife doesn't really talk to him anymore because he spent so much time doing this. It's he said that's one issue, right? There's lots of different. You can put kind of random stuff in here. This one's called pour out. Notice the little spout at the end of the top one. Whoops. Right? Right? You can create your own. You could create your own text files and like pipe it into this program and see what happens. And it's like literally a fluid simulator, which is just physics. Is it accurate? Well, you can see some things like flip out every so often, but it's pretty, I mean, it seems accurate enough, right? He said he had to dig out his physics book to figure it out. But there you go, and there's another one. Just the same program, like nothing, it's just the same program that he's just piping in, right? There's one more that's cool.
What is he typing in each time?
Whatever the picture is, that text gets piped into the program. In other words, run for the program. So this next one's kind of a neat one. It's like, it's a little clock, a little sand clock or whatever, right? Hourglass, right? Pretty cool, huh? So that's this one. He does one more thing at the end here, which does one more thing at the end. He said when he submitted this, he said there's one more thing. He made it color, which is kind of cool too, right? Anyway, so this guy spent plenty of time. You can tell why he won the contest because this is awesome, right? And again, the program itself simply looks like that. That's the whole program that does that simulation.
Wow.
Pretty impressive, right? And obfuscated and et cetera, et cetera. So that's kind of neat. So I'm in the Navy, and I like this kind of thing. Do you guys know that this is back in the day, this is all from. Back in the day when two ships wanted to communicate with each other, and they could see each other through big binoculars, right? People on one ship would have these flags, and they actually still do this. Believe it or not, there are signalmen who still learn how to do this, right? And each flag position says a different letter. So if you want to communicate with a different ship, the guy stands out there, and the other guy has binoculars, and the guy says, OK, this is an A, and this is a B, and this is a C, and whatever, and he spells out whatever they want to communicate, which is kind of neat. Even in today's world, if you if you can see another ship, you don't have to send a radio message, which any ship can pick up, right? So it's actually kind of clever in the sense that they still use it and whatever, which is pretty neat. So people go to boot camp and like learn this stuff. Kind of neat. But anyway, somebody wrote a program that looks like this. Looks like a little flag, right? And that program, when you run it, this is why I like it. When you run it, right, let's see. You can type things like Tufts, Tufts, and see, it's got the little guys. One's like boop, and one's like, boop, and TU, and like F, T, S, and then that means I'm done. And you can type whatever you want, right? This is some more cool flag text, right? And it just boop, and it does the whole thing like that. That one little program, right? This guy won the category. You know what category he won? Best use of flags. Which is pretty good, whatever, right? So that's what this one was. So I thought that was kind of clever. But anyway, if you ever have like 1,000,000 hours and want to do something kind of fun, you can dig into this stuff. But your significant other may never talk to you again. OK? All right. OK, so that's obfuscated C. So let's go back and don't write your programs like that, please. Let's go back and talk about this asymptotic analysis. Recall from 1,000,000 years ago when we met last that asymptotic analysis is how we are able to compare programs and algorithms and functions such that we can say one's better than the other from a speed standpoint. OK? We've got a number of different categories here. The one that we like the most is this constant behavior, which we call order 1, which means no matter how many things are in your data structure, if you're doing some operation and it's constant, that means that it takes the same amount of time if there's 1 element, 10 elements, or 1,000,000 elements. OK? And that's like the holy grail of computer science, right? It's what we're always striving for is this constant behavior. You can't always get that, of course, but that's awesome when you do. Logarithmic behavior is the one where you're breaking things into pieces like half at a time. When you guys play the game, think of a number between 1 and 100, and then tell me whether your guess is smaller or larger. That splits the problem in half if you play it right. You guess 50, and then if I say higher, you guess 75. And if I say higher, you guess whatever between 75 and 100. That's splitting the problem in half each time. What's cool about logarithmic behavior is it is very fast as well, because if you have 1,000, like if I said think of a number between 1 and 1,000, you would only take 10 tries to figure out my number if you played the game right, no matter what, right? So it's a logarithm, in that case the base 2 logarithm of the problem. So that's a good one too. Linear behavior is the one where you have to touch every single element that's in whatever you're doing. Right? If you have to do something on every single element, at the worst case, that is linear behavior. Okay? That just means if there's 10 items, it takes 10 time units. If there's 100, it takes 100. If there's 1,000, it takes 1,000. If you had 1,000,000,000 elements, it's going to take 1,000,000,000 time steps to do that. Okay? Not great, but sometimes unavoidable. And lots of problems actually come down to this. Quadratic was the one where we said that that's starting to get pretty bad, right? This is a case where you might have a screen and you've got 2 dimensions that are roughly the same, and you've got a double, like a nested loop. Okay? So the inside loop has to do n squared number of operations. Okay? So that's what n squared is. This is starting to get not so good. The reason we have fast GPUs is exactly because of this problem. Because your graphics processor has to deal with the screen, which is inherently this quadratic behavior. And so they tried to figure out how to beat that by throwing lots of processors at it. Polynomial is like 3 dimensions, right? Or 4 or more or whatever. Physicists have to do with this polynomial stuff all the time because they live in they work in the 3-dimensional world, right? And so lots of problems are hard because they're take cubic behavior, which is not good. And then finally, exponential behavior, which is the one we really don't like. Okay, I don't really have time today to show you, but if you look up the Tower of Hanoi, and there's a link on the website, you can play a little game, and you might have played it before, where there's 3 posts, and you have these disks kind of grouped up, biggest to smallest. And the idea is to try to get the group of disks from the first post to the third post and moving one disk at a time without ever putting a bigger disk on top of the smaller disk. Turns out, to solve that problem, it's exponential. What that means is for every other element, you double the time it takes. Right? So if you had to do 3 elements, it might take 10 seconds. If you have to do 4, it all of a sudden takes 20 seconds, right? So you've doubled it every time. And so that's really kind of not so fun. Okay, not so fun if you have to do that. And if you can figure out how to get around that, that will be very helpful. There's the Tower of Hanoi link. It's on the website. Okay? All right, let's look at a couple things. Searching through a list. If we have a list, not an ordered list, just a list of, let's say, numbers, and we're trying to find one, what is the best case time it takes to find if that number is in that list? Yeah, 1. Because where would it be? Right at the top. It's the first one right there. It takes best case is constant. That's nice. What's the worst case? What is it? The length of the array, which is, in this case, if we have n elements, it's order n, which is linear behavior, right? That's saying the worst case. Now, normally we care more about the worst case than the best case, because this is the one that'll kill you if it ends up being, if you have a worst case behavior, you could wait a long time, even though sometimes you get best case behavior. We could try to figure out the average case or the expected case. You will postpone that till some other later classes in general. Sometimes we'll talk about that. There's some things with sorting. We'll talk about some average cases. But for the most part, we're going to care about the best case and the worst case in this class. OK? All right. Let's look at binary searching. This, if you look through the program and don't worry about looking through this is just the number guessing program. Exactly what we were just talking about. OK, so what's the behavior of the number guessing program? What did we say that was? Logarithmic, right? This is, if you look through this, see this divided by 2 here? You're basically dividing the problem in half each time. And so that's logarithmic behavior. OK, binary searching, logarithmic behavior. OK, all right. So let's think about some of the, let's put some numbers to some of these things. If we had a 1,000 element data structure, and somehow we were able to code it up so that we could code up all the different algorithms for that. OK, let's say that we had that. I don't know if there are any problems like that, but let's say that we did, and we could certainly fake it out. But let's say we did this. If the logarithmic solution took 10 nanoseconds. Anyone know how big a nanosecond is? A what? It's a billionth of a second. You cannot determine whether a nanosecond, like 1 nanosecond, light goes this far in 1 nanosecond. And light is really fast. Right? So 10 nanoseconds is almost no time. OK? If the logarithmic solution took 10 nanoseconds, the constant solution would take 1 nanosecond. You would not be able to tell the difference between those two, obviously. You also wouldn't be able to tell the difference between these two. Right? Your brain and your neurons and things cannot process anything in 1 microsecond. You just couldn't tell the difference. So even the linear behavior here, you wouldn't be able to tell the difference between the linear behavior and the logarithmic. Great. Quadratic. Now we're getting into 1 millisecond. Guess what? You still can't tell the difference. Right? Even a millisecond, a thousandth of a second, is too fast for your brain to actually do anything. OK, so all these, so even the quadratic one, for 1,000 elements, if the logarithmic only takes 10 nanoseconds, the quadratic is still faster than you care about. For polynomial, and I believe I did this one for cubic, all of a sudden it takes 1 second. Now we're talking about where you can actually figure out some, like you can tell the difference between 1 second and a millisecond, 1,001, right? But still, if your program took 1 second to run, you probably wouldn't care. Like who cares, right? 1 second's like, meh, whatever. If you all of a sudden went to exponential, 10 to the 284 years. Now, that's actually longer than the number of years that have been in the universe by many, many, many orders of magnitude. Right? Even longer than the number of seconds or even probably nanoseconds that are in the universe. Right? So the exponential one, remember, bad. OK? Yes?
What was the A value that got 10 to the 284?
I don't remember exactly, but I figured it out from saying, so let's say the linear takes 1 microsecond, right? If you have 1,000, it's basically 2 to the 1,000 is kind of what it is in this case, right? I think that's how you actually, that's ended up how, I'm not sure that would quite make sense, but it was close to that anyway. OK, a lot of time. Large number, right?
So
large
A
number.
wasn't a large number.
No, A was not a large number. No, I think A was like 2 or something, or maybe 10 or something, but very, like, legitimately small. Don't want to do this one. Now, let's say that we have the same 1,000 element list. And the logarithmic one now actually takes 10 milliseconds. Still very short, right? 10 milliseconds is still pretty darn short. You couldn't tell the difference. For the linear one, all of a sudden we're up to 1 second, right? So just to do the linear one, now you're taking 1 second. Not so bad, right? But the quadratic one, we start getting into some real time here. Quadratic, all of a sudden you're up to 17 minutes. Meaning that if your logarithmic takes 10 milliseconds, you're going to take 17 minutes to do the same thing, quadratic behavior, right? Cubic, 694 hours, basically 700 hours, right? You are not going to want to wait. Well, first of all, you're not going to want to wait 17 minutes for like your program to start, right? You're not going to want to do that in general. You're definitely not going to want to wait many weeks for this, or few weeks for this to happen, right? OK? Exponential, heat death of the universe. The other one was also the heat death of the universe. But this is like really, we're talking, it's just never going to even progress very much. OK? So you kind of get the idea that once numbers get pretty big, you all of a sudden have to think about this stuff. Like it makes a difference. OK? Definitely cubic in this case, bad news. OK? All right. So those are the big numbers. This is just a review, kind of a summary. You can go look at that a little bit later. Basically, the idea is constant, you're not depending on any amount of elements. Linear, you have to depend on every element. Logarithmic, breaking the problem into halves or thirds or whatever. Quadratic is the doubly nested. Cubic is the triply nested. And then exponential is this one where you reduce a problem into like 2 problems that are both bigger than the original problem, right? You're solving the problem, but solving the individual ones actually are more intense than the original. So that's kind of why the exponential is bad news. OK? All right. I asked this question right before the end of the last class. And I said, what's the asymptotic behavior of inserting at the beginning of a linked list? What do you guys think? Everybody think they got an idea? What did you say? Why is it O of 1, Nathan?
You can always access the front of the list.
Yeah. If you have a linked list, right? If you have a linked list, and here's the head, right? What do you have to do to insert there? What do we have to do? Good hand motions. What do we have to do? We have to change the head to point to this one. And we have to, probably in the other order, though. We have to change the next of this one to point there. Did we have to go through and touch any of the other lists? Even though there are a billion other elements. We didn't have to do any of that. This is constant behavior. OK? So inserting the head of a linked list is constant behavior. Awesome, right? It's one of the benefits of a linked list. OK? All right. To insert at the tail, though, you actually have to walk through every element in the tail. Right? So what's the asymptotic behavior there? Order n, right? How could we eliminate order n for inserting the tail? Yeah? Yeah, if you had a tail pointer and you kept it up to date, kind of like what you did in lab, you could actually increase the asymptotic behavior at the end, which is a tail pointer, to constant again. OK? So that's how you actually can make that better, if you keep a tail pointer around. But it's a little more bookkeeping, kind of like what our problem with one of our problems with linked lists anyway. OK? All right, so that's that. To search a linked list, how do we search? If we have 0, 1, 2, 10, how do we see if 10 is in the list? Yeah. You basically walk down the list until you find it, right? OK, so what's the worst case behavior for, what is the asymptotic behavior in the worst case of finding a number in there? O of n, right? Because you might have to go through every single one. What's the best case behavior for finding in a linked list? O of 1. All right, awesome. Okay, because it could be the first one, which is nice. Now, we've said that for dynamic or for arrays, if it's a sorted array, we've got this awesome binary search. Split the list in half, 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 half. Can you do is there a way to do a binary search on a linked list? Not.
Yes, if the linked list is sorted.
OK, walk me through this. This is sorted right here. How do I find out if 2 is in the linked list?
Well, if 2 is bigger than, like, say, well, the median is 1 and 2. I'd say that if it were, like, you had the head and you had the tail value.
Let's say you don't have a tail.
Oh,
Even if you did have a tail.
I would have said that if, like, the number was smaller, you'd go through the head.
OK, let's say that here's what I'm going to do. 0, 1, 20,000, 30,000, and then I have a million more elements, OK? And they're all bigger than 30,000. And I want to search for the number 5. Where are you going to start? Where's the only place you can start? You have to start at the head anyway, right? Even if you had some other way of getting to like the middle here, you've still got to break it in half. But is there any other position we can immediately go to in a linked list? You can't even go to anywhere else in a linked list. So guess what? Is there a way to perform binary search? No. Now, you said almost. They're not yet. What did you mean by not yet? You said not yet.
I said that not yet because, well, a linked list the way we have it right now, you can't go because you don't have a way to get into the middle of it. But if you figure out a way to get into the middle of it without going through every single element.
OK, so if we had something in the middle, let's say that was the middle element, OK, then you could get 1 better than.
No, more as in, let's say you have a way to figure out, OK, this is probably where elements whatever 1,000 is going to be.
OK.
Let's look there.
Yeah, but you can't look there. All you have is a head.
Yeah, that's why I'm saying not currently. I'm saying maybe when we're talking about a very similar but not quite the same structure, there might be that ability. That's why I said not.
Maybe. Now, at the end of the class, we will talk about a thing called a skip list, which has a bit of that property in it. But for what it's worth, if you have one linked list, you're not going to be able to get binary searching at all out of it. Yep. There's no way to make that calculation so that you have unless you keep all the other pointers. And in that case, then you have to think. Then that's basically a dynamic array. Then you've got a dynamic array of all the pointers. So really, you're devolving back into a dynamic array. But for a linked list, no, can't do it. Right? Sad face. One of the downsides of a linked list. OK? Yeah.
How does the Java array list work?
The Java array list is a linked list. It's actually, I believe, a doubly linked list, but it's a linked list. Yep. Wait a minute. No, sorry, I'm completely lying to you. An array list is a dynamic array. It's just a dynamic array under the covers. That's all. Yeah. I believe Java has a linked list, but it's very rarely used. Yeah. OK, so let's talk briefly about a couple other things. What's the key issue when deleting a node in a singly linked list, even if we know the pointer to that node? Let's say there's a singly linked list here, and I say delete this one, and I give you the pointer that shows you that one. What's the issue with that? Yeah.
You don't know what's before it.
Yeah, you have no idea what this one is, and you have to change the next of this pointer to go around it. And so what do you have to do?
You have to get the one right before it.
Right, how do you get the one right before it? Yeah. You can't. So there, but in a linked list, we always have what?
You have the head.
You have the head. So what do you have to do?
Count up to the
Yeah, you have to start at the head and go bing, 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 bing. So inserting into a linked list has this problem of, I don't care if you're giving me the actual pointer you're trying to insert before. You can't or in this case, delete. You can't delete it without traversing the whole rest of the list to the one before that one and getting it that way. So it's kind of ugly, right? Is there a way to avoid this? There is a way to avoid this, and you did this on lab last night. Right? There's this doubly linked list. Now, I won't go over the details because this was in lab. If you have questions about it, come to office hours, look at the slides. But the nice thing about the doubly linked list is that you can go back and forth, and you can you can delete without knowing any of the other direct links around it. The problem with this is totally a nightmare to program, as you found out. It's not a nightmare, but you have cases, special cases, right? Where there's the head pointer's a special case, and the tail's actually not, as it turns out, but the head's a special case. And you have to always change 4 different pointers, and you have to figure out which ones are which, right? And you might have to say something crazy like previous next or something like that. So it gets a little ugly pretty fast. So the bookkeeping is more difficult for doubly linked lists. Okay, once you figure it out, though, it has some benefits. Okay. All right, this is more about which pointers you actually have to change. You did that in lab. Okay. All right, and then special cases with the head, et cetera, et cetera. You can look at this online. All right. Another type of linked list is an interesting one called a circular linked list. What's neat about a circular linked list is instead of, you've got those two, like for a doubly linked list, you've got those 2 null pointers at the head and the tail, and they're null pointers. Why not use them to point to something real? The tail or the next of the tail points back to the head, and the prev of the head points to the tail. And that means you can go to any node and get to any other one by going in either one direction or the other. And you never have to worry about like where directly you are in the list. Yeah?
Could you do binary searching with this? Like, can you start and do one direction at the same time, like both directions at the same time?
Think about what you need for binary searching. You definitely need random access. You need to be able to go immediately to a certain node. You can never do that in a linked list. Right? You can't really go, you always have to start at one and keep traversing down the list. There's no way to jump immediately to one. So no, unfortunately, you can't do that. Yeah. Yeah.
So I know that we don't actually see linked lists all that often in practice, but why would we have a circular list?
That's a good. Why would you have a circular linked list? It depends. Let's say that let's say you had some database or whatever, and it turns out that like the local area around where you are is important. Right? So you end up here, and then you need to get some data, and then you might need something nearby. Well, you can go one way or the other to get nearby. And then even if you're at the end, you've got instant access to the head. And if you're at the head, you've got instant access to the tail. So it's kind of like keeping a head and tail pointer in general. Right? You can also start at one and just go in one direction. If you keep track of the one you started at, you can just go in one direction until you get back to that one, and you've gone through the whole list. So there's no more of this like, oh, I have to start at the beginning. And so there might be some special cases like that. Yeah, you don't see it too often, but there's cases like this. Okay. Let's see. You can have a singly linked circular linked list as well, which basically means you're always going in one direction, but you can wrap back around. So yeah.
So you only have to maintain one pointer through the list if you have a list.
Technically, I guess you only have to keep one pointer somewhere on the list. Yeah, but it's still probably good to keep ahead. You just kind of want to keep ahead anyway. But yes, in this case, whatever pointer you have gives you the whole list no matter what. Yep. OK, so that's circular linked list. You won't see these very often, but you should know about them. Later, we will talk about things called circular queues, which kind of similar idea, but we'll get into the details of those later. OK. All right, some pros and cons. Pros of a linked list. You only have to insert one element at a time. You don't have to do all this big moving of lots of data. Remember, if you're inserting into an array, what's the asymptotic complexity of inserting into an array at the beginning? 6, 10, 22, 5, and 9. If I want to insert right here, what do I have to do? I have to start at the 9, move the 9 over, move the 5 over, move the 22 over, the 10 over, the 6 over, and then put the new value right there, right 9, whatever. I have to do that. That takes how much time? N time. That's asymptotic complexity of order n because you've touched every single one. Okay? Inserting at the beginning of an array, not a very good idea. Inserting at the end of an array is easy. 6. What is that one? Asymptotic behavior. Constant. Okay? So you see that there's some trade-offs there. Some of the cons of linked lists, you can't do binary search. It's always going to be worst case order n for searching. Not a very good thing. Not cache friendly. Don't worry too much about this, but you know when you go and well, maybe you don't do this anymore with laptops and things. You can go and buy more memory for your computer. Okay, you can say go and buy like 4 gigabytes of memory. And it might cost you, these days it might cost you like 20 or 30 bucks. Right? 4 gigabytes of memory, and then you've doubled the amount of memory you have, and that's great. There are actually 3 to 4 different levels of memory. You can only buy the topmost level of memory. The other parts of the memory are like built into the motherboard or built into the actual chip itself. Those are called cache memory. And they're actually, every level deeper you get is faster memory. Now, the question is, why don't you just buy the really fast memory when you want to buy like memory for your computer? I heard it. Who said it? So, yeah, money, right? It costs a lot of money. To buy 4 gigabytes of the really fast memory, first of all, you really couldn't. But if you wanted to, it might cost you like $10,000. Right? So there's a cost thing here, right? What they do, the reason they do that is so that you can have these things called caches. For things you use really often, they get put in the faster memory. So it actually speeds up your overall computer. The problem with linked lists is that when you have these chunks of memory, so remember, an array looks like this, right? An array, you've got a big chunk of memory right there. You can take that whole chunk of memory and copy all those pieces into that one chunk of really fast memory. And you know that it's like in this position. With a linked list, can't we have the first node here, let's say that's 1, and then the next node is way down here, and then the next node in memory might be here, and the next node in memory might be way over here. That actually is what we call fragmentation. And it means that you can't find a little chunk to throw into that fast memory, and it breaks this whole caching system. Okay, so that's one of the reasons linked lists are bad. When you have things that are spread out and not in a nice orderly place in memory, it breaks these like multi-level memories. Don't stress too much about that, but you will learn more about that when you get into like Comp 40 other classes. Okay, and then of course linked lists are definitely more complex than dynamic arrays. Right? Dynamic arrays are pretty straightforward. Linked lists more complex. Pointers and links and nexts and preves and all that. Okay? All right. We already talked about the lab, homework. We already talked about the homework. Again, due Friday night. And hopefully you're working on that. OK, so that's enough about dynamic array or linked lists and asymptotic behavior. Almost every day in here we'll talk about asymptotic behavior in some form or another. So get used to it. Okay? And pretty much in every other computer class you ever talk about. Right? You'll deal with that again. So the next thing we're going to talk about are these things called stacks. Raise your hand if you were in Comp 11 and you talked about the stack. So you guys know something about. Keep your hand up if it was a little confusing. Yeah, I thought so. So we're going to talk briefly about this thing called the stack. But it turns out that stacks are actually an abstract way of thinking about organizing data in a fashion like this, where the only thing you get to do is take things from the top. Okay? So this is like a stack of Legos or a stack of pancakes or something like that, right? Where you've got the top one, and you can't cheat and go down and find some other one, right? You can only deal with the top one. Okay? So we'll get into the details of that. But this is it's an abstract way of thinking about this. Turns out stacks are actually really important, which is part of the reason there is a stack. We'll get into that. Okay? Now, before we get into that, didn't do the Unix tip of the day earlier. I'll do that now. I'm actually not going to. I'm going to kind of skip the Eclipse tip of the day. But let's do one thing with this Unix tip of the day. So one of the things I like to do is show you fun programs in Unix that you might not know about. There are two programs called DC and BC. Okay, turns out that DC came before BC, but we're going to talk about BC first. Okay. If I run the program BC, and by the way, it's on your Mac and it's also on the Linux computers. BC actually stands for bench calculator. Okay, basically, back in the day, there were these calculators, right? And the calculators were I'm talking like 1960s. They had a calculator, and this was kind of a big deal. You know what they used before calculators? Abacuses. Slide, who said slide rule? Did you say that here? Oh, you said slide rules, right? This is, who's heard of a slide rule? Have you ever seen Apollo 13? You know, Tom Hanks and whatever, right? There's a great scene in there where all the engineers, they're trying to figure out they dump all this equipment. It's like one of my favorite scenes in any movie because it's really nerdy and engineering, right? But they're running out of, or they have too much carbon dioxide, and they say, you have this equipment, and you need to go and like figure out how to get the carbon dioxide out of the spacecraft so that they live, and blah, 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 right? Well, and then you have this scene with all the engineers going, whoa, cool, and then they immediately whip out there these slide rules and start going, right? And if you didn't know what a slide rule was, you're like, what are they doing? This is what a slide rule is. It looks like, where did it go? There it is. Looks like this. It's actually two pieces, separate pieces. This inside piece can slide back and forth. And all the numbers on there allow you to do lots of calculations, such as square root, or cubing, or cube root, or logarithms, or all this fun stuff. And there's actually a backside which has even more numbers on it, right? Now, my mom, who knows I'm a nerd, gave me my dad's slide rule from when he was in college. He gave it to me for Christmas, right? And I was like, whoa, that's so cool. And I should bring it in. But I'm looking at this thing, and I've used the slide rule before just because I was playing around with it. And I would figure some stuff, and I'm looking at this slide rule, and I'm trying to figure it out and sliding things, and I can't figure it out. So I go and I look online they have tutorials, right, how to do this. And it turns out that this little slidey piece in the middle can actually come out completely. And you could flip it around, and so it could be in backwards, right? Turns out in my dad's slide rule, it was flipped over, right? And I flipped it back and then could calculate. And I started thinking about it and thought, maybe that's why my dad failed out of engineering school. Because his slide rule was flipped and he never figured it out. And he was, so who knows. But anyway, that's what they had before calculators. And then all of a sudden, calculators came around. And they were not like pocket calculators. They were like desk-sized, right? And they didn't do that much, but they did enough that it was faster than using a slide rule. And nerdy engineers were all psyched about it. So all that said, there's a program that kind of mimics this. It's just a little calculator. Now, BC is your typical calculator. You can type things like 4 plus 5, right? And it tells you 9, which is very nice. And you can type 4 times 5. Let's do this. 4 times 5 plus 3, right? And parentheses work, right? 4 times 8 is indeed 32. And you can do this. And it does other fun things, like it'll do exponential notation and whatever, like 2 to the third is 8, and so on, right? So on and so forth. First of all, the way BC works, you have to know your order of operations, right? Because you need parentheses, and it accepts all that. What's cool about this is it's actually unlimited precision, which means that I can type something like 2 to the 10th, which is 1024, or I could type 2 to the 100th, which is a nice big number, or I could type 2 to the 1000th, which is a pretty big number, or how about 2 to the 10,000th? This is the number, dun, 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 right? And it calculated that pretty instant. I think it's 3,000 digits long or something like that, right? That is a big number. So you can do fun stuff like this with BC, right? You can also put it in what's called math mode, which means that it allows, this would only allow integers in that mode, as it turns out. Put it in math mode, and then you can say scale equals, say, 100. And you can do 3 divided by 5, and it will give you 100 digits after the decimal place, right? Or you could do, say, square root of 2, and it will give you 100 digits of the square root of 2, right? Or you could do scale equals 10,000, and you could do square root of 2. Now, this actually takes a little time to do, right? You could actually tell there was a little delay there. But there's your 10,000 digits after, of the square root of 2. You could calculate pi on this, right? Let's make the scale a little bit more reasonable. Let's say it's 1,000. Turns out pi is the arctangent of 1 times 4. Turns out that's pi, right? If you do that, and the arctangent is a in this, if you do that, it will calculate 3.14159265358 blah, 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 right? Faster than you could do it with a slide rule, or a piece of pencil, or a piece of paper and a pencil, or a desk calculator, or whatever, right? But it's kind of neat. So BC is a neat little tool if you want to do math that involves lots of numbers. Okay? Kind of neat. The other one I want to show you is this calculator called DC. DC, excuse me, DC stands for desk calculator, right? And it came before BC. And DC is interesting in that it accepts things like the following. 4, 5 plus, and then you have to put P to print. 4, 5 plus is the term, and that prints. What you can also do are things like this. You could type, let's see, you could type 12, 5, 3 minus plus. Any guesses what that is? OK, somebody call out the actual number. 10. Any other guesses? $14. Let's see. P 14. Hey. All right. So this is a weird format, right? You can do things like 4, 7 times 5 plus 2, 3 minus divided by. Well, let's not do divided by. Let's do times again, right? P negative 33. Oh boy. So this is a weird format. OK, this is a weird format. We will get to that format a little later in class. But I will tell you that people have calculators like this. I actually have a calculator on my, in my little widgets thing that is exactly like that, right? 4, 5 plus, and it gives me 9, right? This is a special type of calculator, and it actually is what the original calculators, they had to do it this way. But there's some kind of cool things about that. So we'll pause on that and get back to it. OK? All right. Quickly on Eclipse. If you saw me in lab over the last couple days, if you raised your hand and said, my program's seg faulting, first I would probably try to help you look at the code itself. And then if we couldn't figure it out, what did we do? We threw it into the debugger. I wanted to take the time to show you the debugger. I'll do that maybe later. But if you really should learn how to use a debugger. If your program seg faults, the debugger will tell you exactly where it's seg faulting, right? Not necessarily why, but it'll tell you more or less where, and then you can start doing some more figuring out from there. But it's a super powerful tool to help go through your code step by step and to see exactly what's happening in your program at a given time, what all the variables are, what all the pointers point to, and et cetera, et cetera. So please try to start learning how to do that. I'd be happy to show you in lab or in office hours. OK? Homework 2, lots of opportunities to use a debugger, OK? Which is why I suggest Eclipse. You can also use the GDB debugger, which is a command line debugger. But it's a little trickier to get up to speed on. OK? But I'll show you how to do that at some point. OK. Back on stacks. So we have a stack. Now, a stack is one of these abstract data types, right? Which means that all we're doing is defining an interface. What you do behind the covers or underneath the covers is up to you. How you implement a stack, completely up to you. But a stack has 3 operations. OK? It actually also has generally an is empty, but these are the 3 main operations. You can do 3 things to a stack. You can push onto a stack. You can pop off of a stack. And you can do a top on a stack, which means take a look at the stack. OK? Here's how we're going to model it. OK? You can also model it sideways like an array. But for now, we'll just do it this way because it's a little easier to kind of abstractly think about this. 6, 2, 4, 9. OK? Actually, I'll leave the 9 off for now. 6, 2, 4. This is our stack. You are allowed to push something else on the stack. In other words, you could say push 9. And that would say 9 is now here. You could say pop, which says take 9 off of the stack. OK? You could say top, which says what's the top one in the stack, but leave it there. So in this case, what would top return? 4. OK? That's all there is to know about stacks. Right? It's pretty simple in the sense of what the data type looks like. OK? You've got this stack of things, and you can only do things at the top. OK? Yeah?
Is it possible to tell how many things?
It is not possible to tell how many things are in the stack according to our rules. You have no idea, right? You also can't, well, there's lots of other things you can't do. Yeah?
What's the advantage of this structure?
Let's hold off on that question. And I'm going to ask you that question in a minute. OK? Hold off on that. But we'll think about it, but hold off on it. I don't want to just jump into what the advantage is, because you'll kind of see in a second. OK? So those are the only operations. Now, this is called a last in, first out structure. OK? What that means is if you push, 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 if I pushed 6, then 2, then 4, then 9, right? Getting them back out, if I do pop, 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 they come out. The last one that went in is the first one that comes out. OK? That's called a last in, first out structure or way of thinking. You might have seen that in some other classes, right? And some other types of classes where you're talking about this sort of idea of last in, first out. But that's what a stack is. If you push a 6, then you push a 2, then you push a 4, the only way you're going to get back to 6 is if you do pop, pop until you get to 6. OK? Once it's in there in the stack, it's ensconced there forever. Well, until you pop out to get there. OK? So that's the mentality. Now, you're asking yourself, why do we care about this? Why is it helpful to us? Well, turns out lots of problems can be implemented with this model in mind. We'll talk about a few. There are many, many, many more. OK? If we are implementing this, I'm probably jumping ahead a little bit, but I'm kind of getting to your question. If we're implementing this, and let's say we're implementing it with an array, how long does it take to go to the top of an array and pull one off? 01. Well, let's say it's the end of the array. That takes 01 behavior. So popping is 01 behavior. How long would it take to go to that one that you know where it is and see which one it is? 01 behavior. How long would it take to push on there if you did it smartly in the right? You didn't do it where you had to move them all. You just had to put it right there. 01 behavior. Does this answer your question about why it's important to have this kind of structure? In the sense that all the operations we do on this are all constant behavior. I know what you're going to say, but go ahead.
Since those 3 operations aren't on their own very useful, won't you have to do those operations, say, n times to find something?
That wasn't what I thought you were going to say. But that's, it depends what your problem is. There are many problems where this is a great model. And you don't have to worry about the fact that you have something down here or whatever, right? Turns out your problem defines whether you want to use a stack. And it's awesome to use a stack because you've got this great behavior. Yeah?
So another follow-up. Can't you just do the same thing with a linked list?
That was what I thought your question was going to be. Can you just do it? Yes, you absolutely can do it with a linked list. In fact, you can build a stack out of a linked list or a dynamic array or pretty much like other different types of data structures too. But what's nice about it is you have a very defined interface, and it's you don't have to worry about the fact that there's 20 other functions you might have to think about, right? So you can just define it. You can build a stack out of a dynamic array you already have, really. I mean, basically, you just call these different functions. But what's nice is if you figure out the problem you're using uses this, you know that you can always get constant behavior for each thing. So it turns out that it's nice in that sense. Okay? You can define it. And by the way, it would take you 10 minutes to build a stack versus maybe half an hour to build a proper dynamic array. Right? Like, it's just easy because you don't have all those other functions to worry about. It's part of it. Yeah?
Is not being able to access the other elements also useful because you know that it's there?
Well, is not being able to access them useful? In some sense it is, because it makes your problem a little easier. Like you know that you're not going to have to worry about, oh, was I supposed to take the bottom one? Or no. But generally your problem defines it. We'll see the problems in a second that make this easy. Okay? Turns out this is actually so useful that every program you run, and this is what you learned in Comp 11, has this thing called a stack that you're given in your program, and it behaves exactly like this. Okay? In the bigger picture, it's just a piece of memory. But the way it behaves is exactly in this fashion. Okay? And not only that, okay, well, let's see, yeah, I missed this part. Not only that, push and pop are actually so low level and useful for so many things in a computer that they are built in as the lowest level instructions you can have in your computer. Assembly language instructions assembly language code almost always includes the push and pop in their instructions because they're so useful. So you will see stacks being used a ton of times in various other situations. Now, let's talk about one example. This is the one that you might have touched on in Comp 11. If you have some functions here, okay, you have a main function, and main calls function 1 from within main. And function 1 calls function 2. And function 2 calls function 3. Okay? First of all, is it possible if I said, before I call function 1, let's say that I changed this and I said int a equals 3. And then I call function 1. And in function 1, I have int a equals 5. When function 2 returns, let's say I did nothing else but returned. When function 2 returns, what is a equal to again? It's back to being equal to 3, right? So what you can have is a variable here that has the same name as a variable in another function. And they're the same name, but different variables in the bigger picture. What you have to do when you call function 1 is save everything that's going on here, save it in memory, and then let function 2 use all the local memory. And then when function 2 returns, you clean up and you basically restore main. Now, main calls function 1, which calls function 2, which calls function 3. Which is the next one we're going to clean up after we call function 3 when we're returning? Function 2, and then we clean up after function 1, and then we clean up after main, right? And what does that look like? Last in, first out. The last thing that you ended up calling is the first one that gets cleaned up as you go back. Okay? It's just last in, first out behavior. Now, what does this actually look like? Okay, we talked about saving this information. What does it actually look like? Let's see. Last in, first out. It looks like this. Here's a stack. Here's your main function. Okay? When you call function 1 basically, like main basically gets, I should have it over here. Main gets put on the stack. When you call function 1 or function 2, function 1 gets put on. When you call function 3, function 2 gets put on the stack. When you call function, et cetera, et cetera. When you clean up, you do it in the opposite order. And it's this behavior. So right now, you've got main, and then function 1, and then function 2, and then function 3 is doing its thing. When it's done, you clean up and return to function 2. Everything gets cleaned up. This cleanup is all about keeping things in this place in memory called the stack in this last in, first out behavior, like with this last in, first out behavior. Okay, so it's actually kind of a neat way of thinking about it. Okay, so that's how the stack that you might have talked about in Comp 11 like works. Okay, question? I did see the imitation game about Alan Turing. Yes, actually, that's a good point. I forgot to mention this. So Alan Turing was the first. Alan Turing's famous computer scientist. There's a movie called The Imitation Game. Did you see it? It's a pretty good movie, actually. It's with Benedict Cumberbatch, whatever his name is, right? And it's actually a pretty good movie. Historically, there might be little things that need to be changed, but it's pretty good. And yeah, Alan Turing's like a computer science god, right? Unfortunately, he was also kind of driven to commit suicide because he was gay, which is the British government has actually apologized for this and is trying to make amends for what it's worth. But he is a huge, huge computer scientist and came up with the idea of a stack. Called it a little bit different. He said he called it bury and unbury instead of push and pop, which not a bad idea. You're burying the other things underneath the top one, right? So that's that. But anyway, yeah, if you get a chance to see Imitation Game, it's a really pretty good movie. OK, so that's how the stacks work there. Now, as we already said, stacks are so simple that we can pretty easily modify your dynamic array or your linked list to be a stack, right? You just change a couple of the functions around. You say the insert for a linked list or for a dynamic array where we want to remove, add and remove, or push and pop. at the end, so that it's order 1 behavior. For a linked list, at the head generally. If you had a tail pointer, you could do it at the tail. But that's generally where you want to do that. And the asymptotic behavior for those are order 1, right? You want the end of the array, and it's going to be order 1, which is great. OK, and then for a linked list, you want to do it at the tail, and that's also order 1. Okay. Pretty easy to do. You could very easily make a linked list stack or a dynamic array stack. Pretty easy to do. OK, we kind of already talked about this a little bit. What are some of the downsides to using a stack? Somebody who has an answer in a little bit. Somebody from like that corner of the room. What are some of the downsides to this stack? Any idea? 9, 4, 2, 6. Yeah. Alexander. Yeah, well, actually, that's a good point. If you want to access something in the middle and keep everything else, you might have to have a whole other stack to do it if you wanted to, right? You could have another stack, and you could pop off the 9 and pop off the 4 and then get to the 2, right? You could do something like that. But really, there is no random access. No random access. Yeah?
You don't even, like adding on to that, you wouldn't even know where the middle is if you had a stack.
Yeah, you don't know where any of the pieces are. You can't even tell how many objects are in there in general, right? You don't even know that. You can call isEmpty, which is another function, which you can basically say, look, is there anything in there? And if there's nothing in there, it'll return true if you call isEmpty. OK, but that's definitely downsides, right? No random access. OK? Can you search through a stack? Not without getting rid of all the pieces on it, right? No walking through the stack at all. There is no concept for a stack of like walking through it without giving pieces back, right? Without popping things off. OK, so there are some downsides to this. But keep in mind, many problems actually work very well with a stack. So if you have a stack, you can do that. And there's no searching through it as well. OK? All right, now let's get into some examples of where we might use this besides the function pointer one. OK? All right, you know how you go to Kate or Eclipse, and it will tell you, if you like highlight on a bracket, it will tell you what the opposite bracket is that it fits with, right? Like if you highlighted this right here, right, it would highlight this one and say that's the one that corresponds to this, right? Believe it or not, if you type Control-A to select a whole Eclipse document and then Control-I, it will reformat everything and perfectly indent it for you. Just kind of nice, right? And it does that by knowing where brackets are and what the structure of code is. But it finds the brackets. Now, we can actually use a stack to figure out if a program that we give it has curly braces properly formatted. In other words, open parentheses, and then the next thing we see is a closed parentheses, so that's proper. If we had an open parentheses and then an open curly brace and a closed parentheses, that would be bad. Because you can't have a closed parentheses outside of like an open curly brace, right? I want you guys to actually think about this. Take like a couple minutes, talk to your neighbors. How are we going to use a stack to figure out if your braces are properly formatted in this file? And if you don't understand it, ask your neighbor and say, I don't really get it. Do you get it? But if you get what I'm asking, which is basically use a stack to figure out if our parentheses, square brackets, and curly brackets are actually properly oriented in your program. Talk to your neighbor about this. Yeah, question?
Just a
Curiosity.
Let's say you have to move everything in the stack to a new stack and keep it in order.
Yep.
Is that basically the Tower of Hanoi? Is that a conventional behavior?
Is it basically the Tower of Hanoi? If you only had stacks to use, yeah, you'd kind of be in trouble. Because you could, if they had to be in order. Like, what's your overall goal?
You have like a stack of like
No.
numbers that are sorted, and you want to move that stack to a new stack and have it be completely in order. So you would,
If you only had 2 stacks, yeah, I think you'd have to deal with it. I don't even know if it's possible with just 2. Yeah, probably is. Yeah. Okay, who thinks they have an idea of how we're going to go about starting this whole process? Any idea? Yeah.
I think what you could do is you could have an opening symbol, you could put it on top of the stack, and then
Okay, hold on. Every time there's an opening symbol, put it on the stack. Everybody kind of agree with that? Okay, so let's just walk through this. So we see an opening parentheses and we put it on the stack. Good. What's next? What do you think's next?
then basically every time you see a closing symbol,
Okay.
you would compare it to the opening symbol on the top of the stack.
So you pop off the stack, right, and compare it. So we're going. What do we do with the characters that aren't braces or brackets? Ignore them. Okay. So we're going through. We see the I, F, ignore, ignore, ignore. We get to the opening parenthesis. We open parenthesis. Ignore, ignore, ignore. We get a closed parenthesis, and we do what?
You would compare them and see if
So you first pop off the stack, and then compare and say, this is a right parenthesis. Is this a left parenthesis? It is. And then what?
then you can continue on with your now empty stack and find your next opening
Okay.
symbol. And then basically every time there's an opening symbol, you should expect there to be a corresponding closing symbol to follow, because you can't have like a closing parenthesis before a closing brace and you just add an opening brace.
Yeah, that's exactly right. Now, there's one or two other little things that we have to also consider, but that's really the basic idea. Push on opening braces. When you see the closing one, pop off and check and see if it's the same proper closing one. Fury, had a question or comment.
But you have to, like, you only have to check for matching if it's a closing bracket. Like, you can have as many different kinds of opening brackets as,
Yeah, every time you hit an opening brace or bracket, you push it on the stack.
yeah.
And every time you see a closing, you pop off the stack, right? And do that. If you see a closing one, what's the first thing you should really check? Yeah, let's say that I started a program and I said, if that. Well, that's a closing brace. And if you tried to pop off this stack, you'd actually get an error. So what should you check? If it's empty first, right? If you get a closing one, check if it's empty. If it isn't empty, then pop off and check the symbols. Okay? What do you do at the end? What if I had this? If parenthesis, bracket, close parenthesis, end of program.
Well, at this point, you wouldn't get an error because at this point the two that
Oh yeah, that's right. You're absolutely right. How about this way? Push on the curly brace. Push on the parenthesis, open parenthesis. Get to the open parenthesis. Pop off. Check that they're open. It's the right one, and then we're done.
Well, then in that case, right before the end of the program, like right before the semicolon, wouldn't you have another test saying like is empty again?
Right before this, how about after the semicolon? When you're all done, you go back and you say, is my stack empty? Because if it's not empty, we had one extra opening one and not a closing one. Okay? This actually happens more often than you think, because sometimes you forget to put the little final closing brace on there, right? Okay, so that's our algorithm. And this happens to work for a stack really well. First, you make an empty stack. All right. Then you read the characters until the end of the file. If a character is an opening symbol, push it. If it's a closing symbol, and then if the stack is empty, report an error. If you've got an empty stack and you got a closing one, it means you never had a beginning one for that symbol. Otherwise, pop the stack. If the symbol popped is the corresponding opening symbol, or is not the corresponding opening symbol, you've got an error. At the end of the file, if the stack's not empty, you've got an error. And that's your whole algorithm, right? Yeah.
So just like a random question, kind of. But
Yeah.
how does the compiler check?
The compiler does a very similar sort of thing, yeah. It basically goes through and if it gets to the end of your program and it hasn't got a complete program, it'll say something's wrong. It doesn't necessarily check braces, but it does that kind of in the meantime. Yeah. And you should take compiler's class to figure out that. It's a great class. OK, so we just did this. We already did this for this one, right? Well, we didn't actually, but it's pretty much you'd push on the opening parenthesis, then you'd pop it off when you get to the closing parenthesis and check, and they're good. And then you'd push on this one. And you can end up with a number of symbols on here. But each time you get to a close, you pop off, and you're OK. So I'll let you guys walk through this one more on your own if you want to walk through it. OK? All right. Now, let's get back to, well, actually, let me first ask you a question. In the program, if we counted up the number of characters in this program, let's say there's n characters. If n is the number of characters in that file, what is the asymptotic complexity of this whole algorithm? I hear a couple people saying constant, and a couple people saying, what was the other one you said? N. A couple people saying n. Which is it? Yeah. You know what? It's not n because of the for loop, although that's a good idea. It's n because how many times do we touch each character in here? Once, right? So we go through and we touch that character, then that one, and we touch all n characters. And every time we touch a character, it takes one operation to do it because we're just pushing, popping, whatever, right? Or comparing. And really, we don't worry about those other constant behaviors. So you have to touch each one once. So if we had a million line or a million character program, it would take 1,000,000 time steps. If we had a 1,000 character program, it would take 1,000 time steps. So that's a linear algorithm for the whole algorithm. Yeah? No, if they don't match, it's an error. Yeah. If you have a closed parenthesis before you have a closed bracket, you've definitely got an error, right? Because you can't close an internal one with an outer one already, or you can't close an outer one with an inner one open. Yeah, good question. OK, so it's order n because we have to read through every character in the file, and that's n characters. OK, now let's get back to, I promised you we'd get back to this. This way of doing arithmetic that I showed you on the DC calculator, it's actually called reverse Polish notation, otherwise known as postfix notation. It's called reverse Polish notation because the guy who came up with the opposite of this, where you say plus 3, 4 instead of 3, 4 plus, he happened to be Polish. So when you do it the other way, they call it reverse Polish. So you'll see sometimes RPN calculators. That's what it means, reverse Polish notation. We will all generally refer to it as postfix notation. What this is saying, fine, your operands to your operation come before the operator. The operands come before the operator. OK? 4, 5, 6 plus times. 4, 5, 6 plus. The plus refers to the previous two operands. 4, 5, 6 plus means plus or add 5 and 6. That is now 11. So you've got 4 and 11 times, what do? Multiply 4 and 11, because the times comes after the previous two operators. Guess what structure we can use to do this? Stack, right? Unfortunately, the time is not such that you can do it all, like figure it all out. But, or I mean, it's not particularly hard, right? Every time we see an operand, in other words, a number, what do you think we do to it? Push it on the stack. 4, 5, 6. Every time you see an operator, what do you think you do? Pop how many times? Pop 2 things off. 4, 5, 6, you hit the plus, and you go plus. And actually, the way it works is you do this one comes here, and this one comes here. You do 5 and 5 plus 6, and you get 11. So these are now off the stack. What do you think you do with the 11? Push it back on the stack. And then you keep going through, and you get to the next one you get to is the times. And you go, oh, OK, 11 and 4, multiply those. These have come off the stack. And what do you think you do with the result? Push it back on the stack. And then when you're done, when you print the top of the stack. And that actually works. What's nice about this format, OK, what's great about this is that you never have to use parentheses, and you never have to worry about order of operations. OK? It's very nice that you can do that. And it's so easy to use because you've got a stack. It models the stack very appropriately, right? I will let you guys do this one on your own. Go see it. But it ends up being 288. OK? There's no parentheses necessary, which is nice. Perfect simple system for a simple calculator. In fact, there is one of the simple calculators from 1968, the HP 9100A, that used reverse Polish notation. This was a calculator that if you had it on your desk, it was like a status symbol because it cost $5,000 in 1968, which is $34,000 today, right? And if you put that on your calculator, you were able to do calculations really fast, and people go, "Whoa, you're cool because you got this really expensive toy, right?" But you could use it for a lot of fun things. So that's that. OK? All right. Get to this later. Any other questions? OK, I will see you guys Monday.